Hello again. Today I want to show you a very simple example which uses the principle of work and energy to solve for velocity. So here we have this problem. This is slider which is 5 pounds in the weight. So the weight is 5 pounds, and it's being moved from point A, where velocity at A velocity is equal to 0. Let's call that position 1. This is position 1. And then we want to find velocity at B, and we're going to call that position 2. So when it passes position B, we want to find V2, or velocity at B. Now, this is under a constant force. So this force here, this F here, is a constant force. So the magnitude of the force is not going to change. And it's being pulled to the left horizontally. So, using the principle of work and energy, this is a very simple problem. First of all, the principle of work and energy says that work is equal to change in kinetic energy. Okay, and if you put this formulate this, the work, the only force here is this force, but the correct definition of work is F cosine theta, the integral of F cosine theta, integrated with respect to position and evaluated between the 2 points, S1 to S2. And changing kinetic energy would be 1/2 mv2 squared, that's the final kinetic energy, minus 1/2 mv1 squared. And notice here that velocity 1 is 0, so initial kinetic energy is 0. So actually all we have to do is to figure out the work of this force, this constant 10-pound force, and then we are pretty much done. We can go ahead and solve for the velocity at B, or position 2. So now the question is, you could see that here this force keeps, magnitude is the same, but the angle keeps changing, right? So this angle keeps changing. So we have to come up with an expression for cosine theta in terms of this position, changing position. So what I'm going to do, I'm going to draw a triangle here for you, right? You see this height, the 3 feet here is a constant height. If I call this S, and let's say S is measured from here, right? So if we call this S, then the hypotenuse would be S squared plus 3 squared, or 9. And this is the angle theta. And all I need is cosine theta. So cosine theta would be adjacent, which is S, divided by hypotenuse, which is S squared plus 9. So now all I have to do is to put this guy over here, right? And F is just a constant 10 pound, and then go ahead and integrate that. And then I have to determine what S1 and S2 are based on the way I picked my position here. So let me go to the next page. So now we have the integral of, remember the force is 10 pounds. Cosine theta is S divided by square root of S squared plus 9 ds. And then I want to go back and show you what actually the limits of the integral is, the limits of the integral are. So when the particle is here at A, the slider is here, S should be equal to 4, as you could see up here, and then when it reaches B, S would be 0. So actually we are integrating from 4 to 0, and this is equal to 1/2 mass times final velocity squared. Final velocity squared. There we go. So what I want to show you, obviously you can integrate this, there's no big no problem, this is easy to integrate by substitution, but I want to show you actually the outcome of this integral, at least this part, comes out to be equal to 2 if you do the integration and evaluate it between 4 and 0, and then just take the 10 out. So basically we just end up getting a 20 on this side, equal to 1/2 mv2 squared. But look, I want to show you a much easier way that you could do this. A much easier way that this could be done. That doesn't require integrating. So how do we do this? So let me erase this for you here. You see, if you keep track of a point on the horizontal part of this table and find out as this slider moves from A to B, how much this point is going to move along this line, we call this D, then actually the work of this force would be simply F times D. As simple as that, force times distance. And the way you figure out that D is very simple. If you figure out the length of this cord initially, where it's at position 1, so I'm talking about this length, L1, all right? And then figure out the length of the cord when it reaches the final position, which would be BC, and we call that L2, which would be 3 feet. Then D is actually L1 minus L2. So in this case, you could see that L1 is 5, 3, 4, 5, and L2 actually is 3. It's just that distance from C to B. So look, that D is equal to 2. So that's why I knew that the work of this force is going to be simply F times D, and that's a 10, and that's a 2. So the work actually is going to be 20 pound-foot, and this must be equal to what? 1/2 mv2 squared. So of course now go ahead and say 20 equal 1/2. Just be careful with the units. Mass is 5 over 32.2. You got to change that pound to slugs. And if you solve for velocity here, that comes out to be about 16 feet per second. So I hope you like this video and the fact that we use the principle of work and energy, and we can avoid integration. So this concept could be used for any other similar situation, provided that the force is a constant force. So here this 10-pound force was a constant force. Thank you for listening.